Hey guys, this is Alex Panner with Physics 2211, Section MO8, and this is our last lab. And our last lab, my main problem was, can we model someone shooting a basketball using VPython and the physics principles that we know and that we've learned? So the chief result was, once you incorporate a drag force, we can accurately model the flight of a basketball. So to start out, I did a video in Tracker, and this is what it looks like. So here's the video. I used me shooting a free throw, draining it, of course, and the clip is about 1.035 seconds long, and the time step is about 1/30th of a second. And I did a point mass uh, tracking system using the bottom of the basketball because it's easier to see it than the middle. And the ball starts at the origin and goes in the negative x direction and the positive y direction. And I used the height of the goal, which is 10 feet, standard basketball goal, which is 3.048 meters, and I use that to calibrate it. So from the video, we get our data, which we see here in the corner, and we can take a look at that. Okay, so here's our data, and we have you can see in the x-axis, or the component of position in the x direction is negative, and the velocity, which is the slope, is constant. And then in the y direction, you can see the position, which is the blue. You can see it curves that way. So from this data, we can calculate the velocity, the initial velocity in the x direction for our VPython, and the initial velocity in the y. And so what I did is the final position minus, I did delta p over delta t, or delta position over delta t, and you can see here I subtracted it from the initial, which was 0. So I got negative 4.01 meters per second, and then for Vy I get 5.212. So then I used this information and inputted it into what was our lab 5. And so the initial conditions you can see here: the mass of the ball's position starts out at the origin, the velocity, which we just calculated, the delta t is 1/30, which is really small, kind of like the video. And alright, and t goes for 1.035 seconds, and then we have the force of gravity and the force of drag, which here is directly proportional to the velocity of the ball. And then we have F net, which is F of gravity plus F drag, and F of gravity is negative and F drag is opposite to the motion, so it would be positive. And then we use the momentum principle to calculate the position. So ball position equals ball position plus velocity times delta t. So then we extracted this data, and this is what we got. And since the x is constant, we're not really going to look at that. We're just going to pay attention to the y. So originally, we have the tracker data in blue, and I did one simulation with no drag, which you can see here in the red, and then I did one simulation with drag, which you can see in the green, and the green is pretty close to the blue position data, so you can see that drag acts in the y direction. It acts in the opposite direction of the force of gravity. So that's why it falls faster when there's no drag, because there's nothing to decrease the force of gravity. So lastly, we'll take a look at my actual model. And this is what it looks like, me shooting. Here it is. Alright, that's all I have, guys. Appreciate it.